Question number 9 is about geometric progression. The second term of the geometric progression is 16 and sum to infinity is 100. Find the two possible values for this first term. What the authors say over here. If you know the form of geometric progression, that was ar square, ar cube, plus so on, ar raised to the power n minus 1. That is a sequence of geometric progression. R is a common ratio and A is the basically integral multiple of this R. You can also see as a first term. So in a geometric progression, it's given to you that the second term is equals to 16 and sum to infinity is 100. These are 2 points that you have to look here in order to find the solution. What the author demand? Author demand that you have to find the two possible values for this second or the first term. You can see this is AR. No doubt AR, which is equals to 16. You have to find two possible values for that. Means you have to find A in terms of A1 and A2. Means two possible cases you have to find over here. How you can? You have to find this R first, because you don't know what is the common ratio between terms. Specific sequence is not given to you. So look at the formula for sum to infinity, that was about geometric progression. It was S infinity, which is equals to A over 1 minus R, right? S infinity, sum to infinity is given to you, that is 100 over here. So it would be 100, which is equals to A over 1 minus R, right? And one thing more that is given to you is AR is equals to 16. You have to find this R. So if you find this A here, that would be 16 by R. You can do? Yeah, you can do R. So put A is equals to 16 by R in this equation, that is for example equation number 1. Plug in the value of A over here. That gives you 100, which is equals to 16 by R whole divided by 1 minus R. Doing the cross multiplication or a simplification, you can say it gives you 100 is equals to 16 over R times 1 minus R. That gives you 16 over R minus R square. Are you agree? Now do the cross multiplication over here. When you did cross multiplication, your answer would be 100 times by R minus R square, which is equals to 16. So it can be solved further and it can be written over here 25 R square minus 25 R plus 4, which is equals to 0. I did nothing, just only simplify 16 with 100 and then times the term inside, and then my simplified expression would be that one, that is equation number 2 over here. 25 R square minus 25 R plus 4, which is equals to 0. This is quadratic equation. Now I can solve this equation by making a factor. So after making a factor, I can write 25 R square minus 20R minus 5R plus 4, which is equals to 0. This is first pair, this is my second pair. So that would be 5R can be taken as common from the first pair and giving me 5R minus 4 inside. Minus 1 can be taken as a common from the second pair, and inside I have 5R minus 4, which is equals to 0. So that gives me 5R, which is equals to 1, and 5R, which is equals to 4. This gives me R is equals to 1 by 5, and this gives me R is equals to 4 by 5. Now I have two values of this R. I can go back to the question, that was AR is equals to 16. for two different values of r, definitely I have two different answers for a. That was the thing actually that I have to work for. So plug in the relevant values of this r over here. That gives me a of 1 by 5 which is equals to 16, and a of 4 by 5 which is equals to 16 again. Finding the solution, this gives me a is equals to 16 times 5, 80. A is equals to 16 times by 5 dividing by 4, that gives me 20. So this is my first answer 80, and this is my second answer 20. So the possible values for a for this question will be 80 and 20. For the second part, what I have to do, I have to show that the nth term of one of the two possible geometric progression is equals to x raised 4 raised to the power n minus 2 multiplied by the nth term of the other geometric progression. For that, I have to construct two geometric progressions, and then I have to find the multiple of 4 raised to the power n minus 2. And I have to show that that should be nth term of this geometric progression. This is little bit tricky. Two geometric progression you have to consider over here. So first of all, I just make first geometric progression, that is marked as en1. That is a first progression because I have two values of a. One value is 20 and other value is 80. That is calculated in the first part. So by using these two values, I can construct two geometric progressions. So first geometric progression can be written as an1 which is equals to 80 times y r 1 by r, that is 1 by 5 whole raised to the power n minus 1. It would be beautiful to write the general formula for an first. You know that, let me write it with the clear marker. Yeah, this is right. an is equals to a times r raised to the power n minus 1. That is the general formula. So for the first progression, en1 which is equals to 80 times by r value is 1 by 5 for the first one, and whole raised to the power n minus 1. For r is 1 by 5, my a is 80. So I just did put the relevant values over here, nothing else. So doing the simplification gives me 80 times by the value of 5. Yeah, the value of 5. And 1 by 5 whole raised to the power n minus 1. That further gives me 16 times by 5 whole raised to the power n minus 2. I did nothing, just only take one part and outside common and then times by divide by 80 and gives me 16 5 raised to the power n minus 2, nothing else. Now I have to find the second geometric progression, that is an2. And for an2 I have to use the remaining terms of a and r that I have. So an2 would be a, that is 20, and in order to get a is equals to 20, my r value was 4 by 5 in the first part whole raised to the power n minus 1, right? So it can be written as 20 times by 20 can be written as 4 times 5. 4 by 5, 4 by 5 whole raised to the power n minus 1. Again I have to make as 2 minus n so that I can make a comparison. This is my 2 minus n, 5 raised to the power 2 minus n. That should be also 2 minus n so that I can make a comparison or put the relevant values over here. So it's giving me 4 raised to the power n minus 1 times by 4, 5 raised to the power n minus 2. Hope so you understand this step. This is very basic. Just only I just make a power on each term separately. This 4 is as it is like here. This 4 raised to the power n minus 1 is written over here, and this is 5 over 5 whole raised to the power, sorry, this is actually 1 by 5 raised to the power n minus 5, and this is 5. So using the base rule of maths I just did and finding my power as 5 raised to the power n minus 2. Nothing else, the basic maths only. Anyways, that gives me 4 times by 4 whole raised to the power n minus 1 times by 5 whole raised to the power 2 minus n. Now this is same, 5 raised to the power 2 minus n. This is 2 minus n actually. And this is also 5 raised to the power 2 minus n. Can I resubstitute its value over here? 100% I can. This is my en1, so that can be written as en1 dividing by 16, which is equals to 5 raised to the power 2 minus n. I can put this equation number star in equation number double star. So after putting or substituting, I can say that gives me 4 is to the power, again use the base rule of maths, 4 is to the power n minus 1 plus 1. Plus 1 and minus 1 will cancel, and as a whole I have 4 is to the power n. And at that place I can put an1 dividing by 16 can be written as 4 square. I can write it down, an2. So an2 can be written as 4 is to the power n minus 2 an1. That would be my final answer. My requirement was find the integral multiple of 4 is to the power n minus 2, and it should be in a form of nth term. So that is nth term. And also my second term is a product of 4 is to the power n minus 2, and it can be written over here as an integral multiple of the first geometric progression. So it's proved. That's all about that.